All right, so equilibrium tables. I'm probably sounding a bit like a broken record because I keep telling you pretty much every lesson how important all of this stuff is, but I really do need to say it again on this. These tables I'm going to show you how to use today are how you will solve most of the problems for the rest of this unit and all of next unit, and how you will solve a lot of problems on the AP test. So the basic understanding of these tables is going to be very, very important. First of all, the table I've drawn here obviously is typed on your paper, but you are going to have to draw these tables for yourself, okay? When you draw the table, you really only need the boxes. You're not going to need to label what we have labeled right here for all of the descriptions of what's going to go in those rows. But they're just there initially to help you get started. You can write them if they help you, but I think after you do a couple of these problems, you will be just fine, and you won't need to actually write those words out. Now, up at the top of your paper, let's go through and write a little bit more of a description than what's even written in these boxes to help you remember what's supposed to go in each one of these rows. So for the first one where it says reaction, that's going to be where you're going to write your chemical equation. Okay, your chemical equation goes on this line. So let's say we were doing a problem and the problem's equation was 2a plus b is in equilibrium. You see the double-sided arrow because we're doing equilibrium with 2c and say 3b. Okay, so notice each reactant and each product get their own column. That's the point of what I'm trying to show you on there. So each reactant and each product get its own column. You're going to put that balanced equation up in that first box. Now, the next box says initial conditions. For now, we're going to do some other types of problems, but for now, what these are going to be are these are going to be your initial molarities. Okay, your initial molarity. So the problem's going to say you start by putting in blah, 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 blah into your flask. So you're not at equilibrium yet. Okay, those are initial values prior to reaching equilibrium. So maybe the problem tells you you start with 3 molar of A. So you're going to put 3 molar of A here and say 2 molar of B. And so you'll put 2 molar of B. Now, if they don't mention C or D in the original problem as having initial concentration, those ones will just be zeros in those boxes. So anything they don't mention having an initial value will be a 0. Anything they do, you'll put the number in the box. And I actually usually don't even put the unit in there. It needs to be in molarity, but I usually just put the number in the box. Now, the next line, this line that says change, is going to be an algebraic expression. Now, I know that sounds kind of frightening, but it isn't. Okay, here's how you do the algebraic expression. You put, just cross these off, I don't want to do that. Just cross off like that. Okay, so we put an X in each box. Okay, X in each box. Then you're going to look at the coefficient that goes with that reactant. So A had a coefficient of a 2, you're going to make that 2x. B had a coefficient of a 1, so we're going to leave it as x. C had a coefficient of 2, so that will be 2x, and D had a coefficient of 3, so that will be 3x. Okay, so the x in each box, the coefficient from that column goes in with that x. Now, the issue here is that one side is going to be losing and one side is going to be gaining. Okay, so we're going to start with initial conditions, but they're going to be gaining or losing in order to get to equilibrium. So one side has to be positive and one side has to be negative. Honestly, it does not make a difference in your final answer which side you make positive and which side you make negative. I will tell you, to make it easier for us to always match up, if you ever see zeros, see how we have zeros here for these two concentrations? If you see zeros, make that side positive for your algebraic expression and make the other side negative. The reason why I say that is that way you'll deal with positive numbers, okay? And because obviously if you have nothing, the only option you have is to go up. If you have nothing, it can't go down. Okay? So that's the second line. Put an x in each box, put the coefficient with the x, and then make one side positive and one side negative. And again, don't stress too much on the one side positive, one side negative, because it really doesn't matter which one you do. Now the next one, this equilibrium expression line, is really, you're just going to add lines 2 and 3. You're adding lines 2 and 3. So for the A column, we had 3 minus 2x. So I just took these two values and I added them. So for the next one, we'll have 2 minus x. Just added these. I'm going to add these ones. 0 plus 2x just leaves me with 2x. And then if I add this one, it's just 3x. Okay, like so. So 3 minus 2x, 2 minus x, you have 2x, and then you have 3x. All right, and then the last line, this one right here, this will be, it says answer, but really what it is concentrations at equilibrium for each of your substances. Okay, so what we need to do to get this answer, to be able to fill in this box, is we need to figure out what x is. If we can figure out what x is, then we can solve and get a number. And the number would be the concentration at equilibrium. And the final answers, of course, will be in molarity. So this is just really an organizational tool. It helps get all of your thoughts of what's happening, how the equation's going to play into this, and all of that organized. You may be thinking, we haven't even seen equilibrium constant, K, yet, products over reactants. We will. It will be part of the problems. But this is just an organizational tool to get the problems going. Okay, so let me show you what it looks like with a real problem. Obviously, this was all just made up information to sort of give you the basic idea of what it was going to look like. So let's start with this problem. It says, in an experiment, the initial amounts of each of the reactants and products is 0.250 molar. The reaction is allowed to go to equilibrium, so that's telling you the 0.25 molar was before equilibrium. The concentration at equilibrium of NO2 is 0.261 molar, and they want to know what are the concentrations of the other components in this reaction at equilibrium, and also what is the equilibrium constant. So let's just start at the beginning. First thing you're going to do is draw yourself a table. I already have mine drawn on the board, but you don't have that in your space. So go ahead and draw. You need 4 columns because you have 4 reactants and products, and then it's always 5 rows. Again, you don't need to write all of this out, but if you want to, you can. If you need to pause the video to get it drawn, go ahead and do so. Next thing we're going to do is put the reaction in. So NO2 plus SO2 is in equilibrium with NO and SO3. Notice coefficients, it was balanced. The coefficients are all 1s. Next, we want to put in our initial conditions. Phew! Oh, I haven't sneezed in a video in a long time. Oh, thank you, by the way, for saying bless you. All right, so it says initially all of the reactants and products started at 0.25 molar. So what they did was they went to 4 different sources, gathered 0.25 molar of all of these, excuse me, all of these 4 things, and then shoved it all into a container together and said, all right, let it come to equilibrium. So either it's going to make more product or it was going to make more reactant from those 0.25 molars in order to get to equilibrium. And this is going to show us what exactly it did. So start by putting 0.25 in for each one of these. Again, I don't usually write the unit in, just make sure you're in molarity. Okay. Next, you're going to do your change box. So to do the change box, we put an X in each box. X in each box. Now what we're going to do is bring the coefficients down, which happen to all be 1s, so that makes it nice and easy. Then we are going to put our pluses and minuses. One side needs to be positive, the other side needs to be negative. Now for this problem, we have no way of knowing really which side's going to go up and which side's going to go down because there's none of those zeros in here. So just for consistency purposes, will you please make the products positive and the reactants negative in this problem, just so we can make sure we're doing it the same. If you chose the other way around, you will get the same final answer. Your work will look a little different in the in-between parts, but you will get the same answer. Okay, next line, we're going to add these 2 together. So 0.25 minus x, 0.25 minus x, 0.25 plus x, and 0.25 plus x. So again, I just took what I had above each one and added them together. Okay, so now we're at the point where I can't go any further. Obviously, this will tell me my equilibrium concentrations, but I don't have x. I don't know what x is. So here's where we're going to have to do some more figuring out. Let's look back in the problem. I want you to see that they did give us one other given. It says the reaction is allowed to go to equilibrium. The concentration at equilibrium of NO2 is 0.261. So they just told us the concentration at equilibrium of NO2 is 0.261. So find NO2's column. What they just told us was the final answer for this one is 0.261. The reason why that's helpful is that we know that this box right here equals this box here. So in other words, 0.25 minus x equals 0.261. If you take a look at that, we can solve for x now. You're going to subtract over the 0.25. If you subtract over the 0.25, you end up with negative 0.011 molar. That's your x value. Sorry, my negative is way up there. It's kind of weird. Negative, there we go. Negative 0.11 molar. I now know what x is. This is x, this is x, and this is x. So I can go in and plug all those in. So I go for SO2. I'm going to plug in 0.25 minus negative 0.011, and I end up with 0.261. For these ones right here, I'm going to do 0.25 plus negative 0.011. When I do that, I get 0.239. They're the same. So I took being given one, we were given this one right here, and I just set up an equation and solved for x. So if you're given one of the concentrations at equilibrium, the math on the problem is going to be pretty easy. It's going to be pretty straightforward. Now what I'm going to do is take those concentrations. That was the answer to my first question. It says, what are the concentrations of the other components at equilibrium? So this is one set of my answers right here. Then it says, what is the equilibrium constant, K? So we are going to solve. Remember, K is saying the same thing as Kc. We're going to call it a lot of different things, but K, Kc, all the same thing. We're going to be putting our products over our reactants and using their coefficients as exponents. So product is NO, exponent is 1. Another product, SO3, exponent is 1. These are all gases, so we can use all of them. Okay. Remember, gas is in aqueous only. Bottom is NO2, coefficient is a 1, and SO2, coefficient is a 1. So I'm going to plug all of those in. So I'm going to get 0.239 times 0.239 over 0.261 and 0.261. And I'm going to solve for my Kc, and I end up with a value of 0.839. Remember, K does not have a unit. What is that K telling us? Well, notice it's less than 1, right? It's less than 1. If it's less than 1, then that means there's more reactant than product at equilibrium. And take a look back up here. Here's your reactants. There's more reactant than product. Okay, and that's why that K value came out to be less than 1. So this reaction actually went in the reverse direction. When you started with the 0.25s, it went in the reverse direction to get to equilibrium. Okay. So that's pretty much the basic idea of the table. Now, what happens with the math is different depending on what given they give you. In this problem, they had given us this final answer right here. The second problem we're going to do, they're going to give you a different type of information. So let's go ahead to that one. First of all, there's an issue right off the bat before we even get into the problem where you notice the unit is moles and they give you the volume. The first thing we need to be concerned with, the first thing that we need to do is to solve for molarity, okay? Because we need molarity here. So remember that molarity equals moles over liters. So molarity is going to be equal to 0.1 moles over 500 milliliters, which is 0.5. And when you divide that, you're going to get 0.2 molar as your molarity. Okay, 0.2 molar. And again, we want the molarity, not the mole value. All right, so let's set our table up. You need to draw your own. I'll tell you that my one that I cut and pasted in here actually has one too many columns. We only need 3 columns because we have Br2Cl2 and 2BrCl. And again, you don't have to draw this part onto your paper. If you need to pause so that you can get that written in, go ahead. We'll start by putting the equation on this line. So we get Br2 plus Cl2 is in equilibrium with 2BrCl. We're going to write down our initial values. Notice the only thing they introduced into this flask was the product, BRCL. So the only thing that we have a value for is this product at 0.2 molar. So we're going to put zeros in for these ones. Okay, so anything they don't tell you about, you're going to put zeros in for. Now notice in the problem they've told us the equilibrium constant, and they want us solving for what's going to eventually go in these boxes. So we need to fill out the table. From this point, just to fill the table out, we actually don't need the problem anymore. We're going to put an X in each box. Okay, you're going to bring your coefficients down, so a 1, and a 2. I'm going to make one side positive, one side negative. I have zeros this time, so again, on the 0 side, make those ones positive. It helps avoid dealing with negative x's, which obviously is just a number, but I think it just makes it a little bit simpler. Now we're going to add line 2 and 3. So 0 plus x equals x, 0 plus x equals x, and then 0.2 is going to be 0.2 minus 2x. Again, we're adding them together, but the x was negative, so it'll be minus 2x. So that's what we have so far. Now, unlike the last problem, this one didn't tell us one of these 3 answers. So we don't get to just set up a little equality and solve for x. This time, the additional piece of information that was given in the problem was the value of k. So how will that be beneficial to us? Well, let's think about what k is. Let's write our expression for k. Remember, we were looking at phases. All of these phases in this problem are all gases, so they're all going to be included. So you're going to have BRCL. Now, the BRCL is on top because it's the product, but look at its coefficient. Should have a square on it in the K expression. And then BR2 has a 1, and CL2 has a 1. All right, so looking at that equation, still, you might be thinking, what is that going to do for me? Well, we know that Kc, looking back up at the problem, we know Kc is 6.9. So instead of Kc, I'm going to plug in 6.9. Now, I don't know what these concentrations are. They're what I'm trying to solve for, but I do have variables that represents each one of them. So instead of BRCL, I know that this expression equals the answer. I just don't know what x is yet. So I'm going to plug in up here 0.2 minus 2x, and that value is squared, because again, that inside the parentheses represents a concentration, and then that concentration is going to need to get squared. For BR2, x is what the concentration will be. I just don't know what x is yet. So I'm going to call that x. And then for Cl2, I'm going to call it x. So now I have a variable expression with lots of variables in it, but they're all the same one. They're all x's, which means we can solve this problem. Okay, this is where your algebra skills are going to come into use. Now, some of you may be taking a peek at this, and you might be having some fleeting thoughts of the quadratic formula. Does this look like it could be a quadratic formula problem? Well, honestly, I'm going to show you how to do this one without quadratic. But I'll also be honest with you and tell you, yes, we do use quadratic. And we will be using the quadratic. Hopefully you have it in your calculator. I'll talk to you about this a little bit more tomorrow. You will be able to use a program if you have one in your calculator. So if you do not have a quadratic formula program in your graphing calculator, I would suggest getting one, okay? Because I will allow you to use it. The AP test allows you to use it. But what I was saying before is we actually don't need it in this problem. This one actually will be easier than that. If you look on the bottom right here, you have x times x, which really is the same thing as saying x squared. Okay, so instead of calling it x times x, I'm going to call it x squared. Since both of my values on this side are both squared, really what I can do is just take the square root of both sides. If I take the square root, let's start on the 6.9 side. If I take the square root of 6.9, you get 2.6268. Over here, if I take the square root of something that's squared, it cancels off the square. So it'll leave on top 0.2 minus 2x, and then on bottom it will just be x. Okay, so again, the square root canceled those squares out. If you didn't know that mathematically, I would suggest going back and rewatching that part again, okay, because that's just some basic algebra. Now you're going to cross multiply. Okay, so we'll do 2.6268 times x, and that equals 0.2 minus 2x. So again, I just cross multiplied. I did this times, and this is over 1, of course, times this. Now I'm going to combine like terms. Okay, so I'm going to bring this minus x over to this side. So that gives me 4.6268x. is equal to 0.2, like so. And then I'm going to divide over my 4.62 number, and I'm going to end up with x being equal to 0.0432 molar. So it looks like that. So that is not your final answer. However, that is what x is. This value right here, we need to go back up into our equation, and we're going to bring it up here. Bringing it up here, and we're going to plug in to those expressions for x. So both the first two actually are just x. That makes it nice. So you're just going to plug those in. So there's one of them. And then this one we're going to actually have to plug in 0.2 minus 2 times our x value. If you do that in your calculator, you will get 0.114 molar. Okay? So those right there, there's so much writing in here. Let's do it this way. Those right there are your final answers. Okay? Now there is a way to check your work once you've done this. If you take those concentrations and come back and plug them into your Kc expression, so do 0.114 squared, and then down here 0.0432 and 0.0432, and solve, you should end up with 6.9. Or very close. Rounding, it could be off a little. And that's always a nice way to check. You know, if you have that ability to check, then we should. All right, now there's one more problem on your paper. This problem is going to involve more math than what we've just done. It's going to involve the quadratic. We're going to have to do a lot more with it. What I want you to do right now, and this will be your only homework, if you feel like you didn't understand something on the video, you should go back and rewatch it, okay, or watch the parts that you were struggling on. What I want you to do on this third problem is I want you to just go through and plug in the, what I have essentially here in blue, okay? I want you to go in and plug in the reaction. I want you to draw your table, plug in the reaction, plug in the concentrations, do your change line, and do your fourth line, okay? Don't worry about solving yet. You're welcome to try. If you would like to, please go ahead and do so. We will do this problem first thing tomorrow together. I want to walk through that one because there's a little bit more math to it. But again, you should be understanding how to set your table up at this point, okay? The ways to solve for x vary, and we're going to still work on that. But you need to be able to